You need to get 80 plus in paper 4 to be safe in my mocks. কারণ তুমি এখানে 80 plus যদি না উঠাতে পারো, how are you expecting to get 70 in the actual exam? It's like a much more easier environment to give the exam in. Actual exam are complicated হবে. So a buffer রেখে mark নিতে হবে. So buffer হচ্ছে you need to get 80 plus. I don't know what happened with you. No, the 55 is supposed to be a good number. Yeah, what happened? তোমার তো MCQ খারাপ ছিল না 30. It was the practicals. এখন প্রবলেম নেই, এখন practicals নাই.
At this position,
হ্যাঁ মানে A star A হয়ে গেছে, A হচ্ছে B হয়ে গেছে। না না সবগুলোই নেবে। হ্যাঁ প্রিভিয়াস গ্রেড চেঞ্জ হওয়া না, ওটি কেন হবে? ওটাই থাকবে। ওরা জাস্ট পার্সেন্টেজ ওয়াইজ হচ্ছে ওইখান থেকে অল্প পার্সেন্টেজ নেবে, ওরা ওইখান থেকে নিবে। কারণ you get a grade on your entire A levels. Oh no, ওরকম না। much bigger weight on your A2 papers. So paper 4 is everything. Paper 4 I think is like 46.67% of the entire grade. So it's like almost 50%. We practical paper can be only 7%, 13%, 11% এরকম। P5 হচ্ছে বাকি যেটা, but yeah, the paper 2 like paper 4 is everything. So paper 4 ভালো করলে ওগুলো এমনি cover up হয়ে যায়। Right, October, November 4-2. Which question? Last year মধ্যে this one. Number 8. Okay, so quantum physics তোমাদের হচ্ছে just বলে রাখি আমাদের এই book 2টা is like to AC cards, তারপরে থাকে quantum mechanics or quantum physics, nuclear physics, medical physics, space physics, ওগুলা সবই করতে হবে because it's মানে you do every question, not any selected question, as many you can do. These are completely new topics for you. Magnetism বা যা করে আসি so far you had them from your O levels, but quantum absolutely new. Nuclear physics you don't have radioactive decay, but that's the new version of it. Medical physics is just you have to memorize, and math, and you're going to get a question on medical physics for sure. That's inevitable. Astrophysics take a question, Baba. Astrophysics question so far I've noticed that they're manageable, but they're nothing out of the ordinary. Problem with the quantum or nuclear, so you try to be focus karo. No, so the question paper, right? So we'll be doing 22, 23, 24 যত quantum and medical book বানানোর মতো question না, because medical physics completely changed হয়ে গেছে। Okay, before we start, let's just do a quick reminder. Tell me 5 equations from quantum physics. Let's start with the one that changed everything. No, it's not this. There's some other chapter. What is the go-to equation in quantum physics? Yes, E equals to HF. E equals to HF এর মধ্যে হচ্ছে, why is this important equation? Because this equation tells you that light happens to be a what? A particle, right? And the energy of that particle depends on the what of the wave, the frequency of the wave, right? So E equals to HF first equation that you need to know. Then next, Sarka, tell me that equation that relates to a wave-particle duality. Very good. Lambda equals to h by p. Lambda equals to h by p ki bole that a particle can have a wavelength and a wave can have momentum, right? And lambda equals to h by p, where lambda is there's a name for that wavelength, ki, de Broglie wavelength, and p is your what? Momentum, right? And in E equals to MC, I mean, you can equate these two and derive them, but you need to know one of them. Right, so ekhane lambda hocche wavelength. Now wavelength of what? The particle. And the P is the momentum. And what is H? Planck constant. Value koto? Right, good. So 6.63 into 10 to the power minus 34 joules second. Lambda is de Broglie wavelength. De Broglie wavelength tells you that, it's the wavelength that you need to have to exhibit what behavior? Wave-like behavior. So can you tell me when does a particle turn into a wave? Yeah, so when the de Broglie wavelength is less than or equal to your what? Gap size, okay? So এটা যদি achieve করতে পারো, then you will undergo diffraction. Right, tell me the next equation. Equal or less than? Equal হলে তো হয়ে গেল, so less than করে আর দরকার নাই. So minimum হচ্ছে equal হতে হবে. হ্যাঁ, because ওরা জিজ্ঞেস করে যে electrons diffract in salt crystal. So salt crystal সব গ্যাপ তো একদম equal নাও হতে পারে, ছোট হতে পারে. Okay, what's the other one? তাড়াতাড়ি কোয়েশ্চেনটা করতে হবে, আমি তো এখানে রিক্যাপ করতে আসিনি। No, ওইটাই, yeah, exactly. So phi first, work function is hf কি হবে? T being your what frequency? Threshold frequency. And when you put everything together, you get this equation. hf is equal to phi plus half m v কি হবে এটা? Max squared. Okay, this is when photoelectric emission takes place. These are the equations that you have. E equals to mc squared also এটা তো এই চ্যাপ্টার না, এখানে কোথায় ইউজ করতে চাও? Like where do you want to use this? এখানে তো কোনো স্কোপ নাই। ওইটা হচ্ছে from the chapter nuclear physics, where mass can be converted to energy and হচ্ছে produce energy during interactions, right? আচ্ছা, anyways, এখানে বলছে show that the momentum of a photon in an electromagnetic wave is p equals to h by lambda. So momentum is what? Mass into velocity. আর হচ্ছে আমাদেরকে কি করতে হবে? h by lambda. How do you show this? মানে ওরা এই ইকুয়েশনটাকে শো করতে বলছে, কেমনে করবা? How? E equals to E equals to mc square, and E equals to what? hf equals to mc square, and আমার দরকার এখানে হচ্ছে momentum. So that right, equals to mc, so mv into v. What is mv? Right, p. So hf equals to p times v. So p equals to hf by v. আমার এখানে frequency by velocity কি হবে? Lambda. V equals to f lambda, right? So therefore p equals to h by lambda. Okay, so you just equate these two equations. Right, so E is the energy that anything possesses, right? And hf is also the energy that anything possesses. However, there's a catch. This energy E is for a particle because it needs to have what? Mass, right? And this energy hf is for what? A wave, because it needs to have a frequency. But we understand that wave and particle duality tells that they can go from one to the other, which means both the energies need to be what? Same. That's why we equate them. Oh no, ওটা তো nuclear physics এ। Nuclear physics এ যখন একটা রিঅ্যাকশন হয়, ওই রিঅ্যাকশনের মাস বিফোর মাস আফটার ডিফারেন্ট হয়, ওই গ্যাপটাকে আমরা মাস ডিফেক্ট ডাকি। ওটা নিউক্লিয়ার রিঅ্যাকশনের মধ্যে কতটুকু এনার্জি রিলিজ করা হচ্ছে বের করার জন্য। not here. ওটা তো হচ্ছে E equals to del E is equal to del mc square, and this mass is the mass defect. This formula of E equals to mc square, it is not from radioactivity, not from particle physics. It's just a general equation for energy mass interaction. সব জায়গায় ইউজ করা যায়। আমি তোমাদেরকে বলছি এখানে ইউজ করতে না, বিকজ আমাদের কোনো কোয়েশ্চেন আসে না যে এখানে ইউজ করতে হয় এখানে। That's why in our syllabus E equals to mc square is more inclined in the chapter of radioactivity or nuclear physics. Okay, use the expression in AI to show that the photon in free space has a momentum of that much. So, কি করব আমরা? Just হচ্ছে P equals to H by lambda. আমাদেরকে বলছে that a photon in free space has of red light. আচ্ছা, red light. So এখানে কিছু একটা করতে হবে আমাদের. So what's H? 6.63 into 10 to the power minus 34 divided by the lambda belongs to which wave? Red light. Do you know what the wavelength of red light is? You have to know that. 700. That's a 700 to get 300 is the range. 300 is violet and 700 is your red, right? So 700 into 10 to the power minus 9 because nanometer to meter নিয়ে যেতে হবে। এটা করলে যেটা আসে should be the answer. ওরা বলছে that has a momentum, exact number চাচ্ছে। এটা চেক করে দেখবো কি কত আসে exact। Is they're looking for an exact number. That's a little strange. Red light to ধরো এটাই আসে। আচ্ছা, what if you find the wavelength using this value? Then how do you confirm it's red light? আচ্ছা, হ্যাঁ, I think করা যায়, বাট আমি তোমাদেরকে বলছিলাম যে রিভার্স আর্গুমেন্ট গুলো একটু ইস্যু হয়। রিভার্স আর্গুমেন্ট জিনিসটা হচ্ছে তোমাদের দেখিনি, বাট এডেক্সেলে দেখছি যে ওরা বলছে শো দিস, তুমি ওইটা ইউজ করে অন্য কিছু শো করছো, রাইট? মার্ক দেয় না, because they want you to end up with this as the final answer, not use this to get somewhere else. Though logically it means the same. If A equals to B, B should be equal to A, right? But এডেক্সেলে the paper দেখতে পারি তো ওইখানে ওরা মার্ক দেয় না। তখন যেটা করতে পারো is like secretly do it, and then write that, oh, this is the wavelength, and then do the math forward. Don't show it to them. Right, so a beam of red light of intensity 160 watt per meter square is incident normally on a plane mirror as shown in figure 8.1. The momentum of each photon in the beam is provided here. All of the light is reflected of the mirror in the opposite direction in the original path. The cross-sectional area of the beam is provided. ওরা বলছে যে তোমাদের বের করতে হবে show that the number of photons incident on the mirror is that much. এটা easy আছে, এটা কেমনে করব আমি বলি। We know the power there you can actually find number of photons. Okay, so power dawa ekhane power is 160 watt per meter square, so 160 watt per meter square আসছে। Number of photon incident on the mirror per unit time, is it 160 on the mirror? How do you find number of photons using power? It's red light, right? So that's something we know. So how do you find the number of photons here? কি করব? Work done. What's the first thing we do? আচ্ছা, তোমাদের এই চ্যাপ্টারটা মনে হয় ওরকম এনাফ করা হয় নাই, বিকজ যেটা we did this in class, but মনে নেই তোমাদের। whenever you're given power, number of photon বের করাটা খুবই ইজি। কেন? because power 160 watt means what? That the number of photons that are bringing in, how much energy are they all bringing into you every second? 160 watt. So we know that 1 second our energy আসছে 160 watt, and x number of photons every second must provide me how many joules? 160 joules per second, right? Now I need to know the energy that one photon brings me. That's a very easy thing. What is it? Yeah, equals to hf, right? So energy of one red photon should be hc by lambda, or hf, hc or 6.63 into 10 to the power minus 34 into what is c? 3 into 10 to the power 8 divided by what's lambda? 700 nilamambra into 10 to the power minus 9. Can you see what the energy of a single red photon is? single red photon energy? (2.84 into 10 to the power minus 19). Right. So if one of them provides this much energy, 2.84 into 10 to the power minus 19, how many of them would be needed to produce 160? Unitary method, right? So X is going to be equal to 160 divided by 2.84 into 10 to the power minus 19. How much is that? (20) or কি বলছে? Per unit time, number of photons. Area issue আছে একটা মনে হচ্ছে দাঁড়াও। হ্যাঁ, প্রবলেম নেই। কত আসছে এটা? হ্যাঁ, সো কত আসছে এটা? 5. 10 to the power 20. Okay, problem নেই। Photons, this one is beaming onto your plate of what size? Yes, এখানে উপরে. What's the size of the plate? 1 meter square. But is my screen or mirror that size? No, it's how much? 2.5 into 10 to the power minus 6. So our RT unitary method করব. So X equals to 2.6 into 10 to the power minus 6, right? Meter square. So basically উপরের নাম্বারটাকে into 2.6 into 10 to the power minus 6 করলে যা আসে। There might be an easier way of doing this, but আগে দেখে নিই answer আসে নাকি। 1.5. 4.6. আচ্ছা, maybe ওই round off গুলো ওদিকে একটু এদিক ওদিক হয়ে গেছে, but that's how you do it. আচ্ছা, so এখানে for 2 marks it feels like a lot of work to do, so একটু দেখে নিই কোনোভাবে শর্ট করা যাবে কি জিনিসটা। Typically they shouldn't, if it's because of rounding error, but if it's because of like a mistake, then of course, but rounding error এর জন্য পাওয়ার কথা না। So instead of finding the energy, we find the total energy that you achieve in that area. Yeah. So যেটা করবা, power equals to energy divided by what? Or sorry, intensity. Intensity equals to power by area. So আমি পাওয়ারটা বের করে নিব, the actual power that I get. Actual powerটা কত বের হবে? So it was how much? 160 into what is the area? 2.6 into 10 to the power minus 6. এটা দিলে আমাকে ওয়াটটা আসবে, তারপর আমি হচ্ছে এই ম্যাথটা করব। তাহলে it's the same thing by the way. Okay, এই ফর্মুলাটা কিন্তু একটা ইউনিটারি মেথডেরই ডেরিভেশন। So that's how you get the answer. Use the information to determine the pressure exerted by the light beam on the mirror. This one is an interesting question. How do you find the pressure exerted by light on a mirror? So pressure formula key, force divided by area. We do know the area on which it's hitting. 2.6 into 10 to the power minus 6. How do you find the force that photon exerts? What do you do? Very good. So we know the momentum somewhere here is this one, right? So rate of change in momentum. How do you find the rate of change? Momentum divided by time. What's the change? Momentum. So it's coming in with this momentum and it goes out with what momentum? Same. কারণ আমরা বলছি opposite direction এ একইভাবে যাচ্ছে, right? So if it comes in with 9.5 into 10 to the power minus 28, it will go back with how much as well? 9.5 into 10 to the power minus 28. So that's the change over what time? 1 second, because we took the whole motion as the time of impact, right? So you cannot say it's going to be 9.5. 9.5 into 10 to the power minus 28 minus 9.5 into 10 to the power minus 28 divided by 1 হবে এখানে, right? So এটা করলে যেটা আসে should be the pressure. Okay, বুঝছো এটা কি করতে হইছে? The beam of red light is now replaced with a beam of blue light of the same intensity. Suggest and explain whether the pressure exerted on the mirror by the blue light is less than, same as, greater than the pressure exerted by the red light. Tomorrow to figure out. So red light ke jo blue light they replace kori of the same intensity. How does the pressure compare? Momentum increases. More pressure. Momentum equals to h by p equals to lambda equals to h by p. So p equals to h by lambda. Blue light has a shorter wavelength. So what momentum? Greater momentum. Pressure equals to force by area, which is change in momentum by time by area. So momentum যদি বেড়ে যায় তাহলে আমার কি বাড়বে? Pressure. Okay, that's it. বলো অন্য কোনো কোয়েশ্চেন থাকলে। This one. Okay, it says nucleus Z undergoes nuclear fission to form strontium and xenon, according to this equation here. The figure 9.1 shows the binding energies of strontium-93 and xenon-139 nuclei. The fission of 1 mole. Question. I want everyone to try this. Okay, so it's a standalone question. I don't think you need any information from behind. So determine the binding energy per nucleon in MeV of Z corridor. There's a formula that you need to know to solve this question. E equals to mc squared. That's it. R92. Okay, so that's the only thing you need. Our each log. So bear korto. কিসের ভ্যালু চাও? Yes, answer. -1.28 -12. -7.4 MB best objective. 1.2 into 10 to the minus 14 or 13. 12. Are the table values not binding energy per nucleon? No, just binding energy. Total. MEV তে কত আসছে? 4. And the actual answer? No, that didn't match. But how's the other one matching?
-1.18.
আচ্ছা করে দিই এটা। আসছে অ্যান্সার কারো কিছু? No. So এখানে বলছে you have strontium here, xenon here, and 2 neutrons generated, and Z হচ্ছে যেটা is producing this. ওরা বলছে that the fission of 1 mole of Z releases that much energy. So 1 mole of Z is releasing this much energy. Find the binding energy per nucleon in MeV of Z. So first of all, we know the binding energy for strontium, and we also know the binding energy for xenon. আমাদেরকে যেটা বের করতে হবে, what's the total energy that's released in the process? How do you find this? So what's the formula for binding energy per nucleon, or binding energy formula key? Yeah, so binding energy is equal to mc square, mass defect দিয়ে। এখানে হচ্ছে we have strontium, which is 93, our binding energy provide করা এখানে, and xenon, which is 181, binding energy provide করা, or also determine binding energy per nucleon of this releases that much energy. One more that. So এটা চেক করে দেবো কত আসে। আমি আগে অ্যান্সারটা করে নিতে বুঝেছি তোমাকে।
They should be produced for release the API and
Fission. No. Binding energy বেশি হবে per nucleon, not total energy. এটা চেক করে দিবা কত আসে এই ম্যাথটা into 10 to the power minus. এটা কি ছিল Z strontium Z এর নিউক্লিয়ার নাম্বার কি হবে 93 plus 139 plus 2 minus 1, right? So 93 plus 130 or 233 plus 2 minus 1. So this is 2.77 into 10 to the power minus. I'm just check answer 233 কত আসে এটা minus 12. This is what you got. আচ্ছা ঠিক আছে right, so এটা হচ্ছে in joules. এখন 1.19 into 10 to the power minus 12 কে আমরা হচ্ছে যদি EV তে কনভার্ট করি 1.61 into 10 to the power minus 19. How much is it? 7.4. Into 10 to the power 6. Asha 7.4. Okay. Okay, let me explain কি হচ্ছে so সবাই একটু ইকুয়েশনটা দেখো let me show you কি হচ্ছে এখানে so you have this one nucleus of Z which is unstable তারপর আমরা একটা কি ফায়ার করি towards the nucleus a neutron and as the neutron collides with it what happens that it becomes very unstable and it breaks down into pieces and this process is known as what nuclear fission যখন হয় what happens to the particles that are generated in the fission process are they more stable than before or less stable more stable মানে their binding energy per nucleon is going up because if you remember the graph here এই যে গ্রাফটা এরকম দেখতে এটা এই যে like that right so you're here somewhere and your aim is to go that way so it becomes more stable and what happens is it releases energy in the process কেন energy release করে কেমন এটা বলতে পারবা it's a very basic very common phenomena of all the interactions like fission and fusion the energy release হয় কেন energy release হয় it's like a fundamental requirement and I find that students don't get it তার জন্য একটু বুঝতে প্রবলেম হয় why is energy released why is it that hydrogen merge করে যখন helium হয় energy release হয় আবার uranium break করলেও energy release হয় like energy is always released it's not like the chemical version of bond making and bond breaking ওখানে energy নেওয়া হয় energy দেওয়া হয় এখানে whatever you do energy দিচ্ছে ছেড়ে দিচ্ছে কেন lower energy value more stable হ্যাঁ হ্যাঁ আচ্ছা কাছাকাছি actually reverse argument right but you're not wrong as well আমি একটা জিনিস বলি তোমাকে এটা I think will help you clear out things এটা লিখতে পারবা না এটা just বুঝার জন্য so the more stable nucleus the less energy it needs to be stable আবার রিপিট করতেছি the more stable a nucleus the less energy it needs to be stable এটার analogyটা হচ্ছে when you have a very stable equilibrium system in physics right ওটাকে equilibrium রাখার জন্য এফর্টটা কম লাগবে as opposed to something that's in full chaos it's rolling around moving around falling around ওটাকে equilibrium রাখতে হলে আনতে হলে বেশি এনার্জি এফর্ট দিতে হবে it's like let's say you have this calculator এটা যদি একদম stable থাকে it's somewhere there একটু এদিক ওদিক গেলে I just need to do like a small amount of push to keep it stable but if it's somewhere here Don't I need to do a lot of work to bring it back to stability? So the closer you are to a more stable nucleus, the less energy you need. So tomar jeta hoy, now why did I show this? Everyone wants to become what? Iron, right? So the smaller ones, when they're moving towards the iron, or they're joining together. And as they keep joining up, they become more stable, their nucleus. And as they become more stable, do they need all that energy to keep them together? Or they require less energy? Less energy. যখন তার জন্য যখন উপরের দিকে যায়, ওরা কি করে? ওদের এত কিছু লাগে না. Some of the energy is actually released. But on the other hand, the bigger ones, they are also unstable. And when they break down, let's say এখানে strontium form হচ্ছে, xenon form হচ্ছে, ওদের version is more stable than whatever Z is, right? So again, এখানে কি করা হচ্ছে? Energy release করা হচ্ছে. এটা multiple different ways এ approach করা যায়. আর একটা example হচ্ছে nuclear structure. Did I tell you about the magic numbers? মনে আছে magic numbers? So magic numbers গুলো কি ছিল? That a certain number of nucleons will make your nucleus more stable. Then it's like surrounding nuclei out there. So a magic number যখন set করে, structure becomes very stable. When every nucleon is like attached in such a way that geometric ভাবে it's an ideal shape. ওটাকে stable রাখার জন্য energy বেশি লাগবে না কম লাগবে? কম লাগবে, because it's naturally like the বলি, and then I found that students find it easier. তোমাদের এটা লেখার কোনো স্কোপ নাই, জিজ্ঞেস করলে এটা লিখতে পারবে না। আচ্ছা, সো এখানে যদি জিজ্ঞেস করে যে, আর তোমরা যদি চিন্তা করো যে কেন স্টেবল হয়ে যাচ্ছে, মানে স্টেবল হলে কেন এনার্জি রিলিজ করে, দ্যাটস দ্য কোয়েশ্চেন, রাইট? সো অ্যাজ ইট বিকামস মোর স্টেবল, লেস এনার্জি ইজ নিডেড টু কিপ ইট স্টেবল, অ্যান্ড ইফ লেস এনার্জি ইজ নিডেড টু কিপ ইট স্টেবল, ও তো সারপ্লাস এনার্জি নিয়েছিল আগে, ওটা লাগতেছে না, ছেড়ে দিচ্ছে। And that's where energy is released when you combine, known as fusion, or you break down, known as what? Fission. So both sides say energy ছেড়ে দিচ্ছে, because you're becoming what in both the cases? More stable. Okay, so এখানে যেটা হচ্ছে, let's get back to our question here. এখানে হচ্ছে whatever Z was, right, it became these two, right? A strontium or xenon. These must require actually what energy than that to be stable? Less energy. স্টুডেন্টদের ওইটা কনফিউশন থাকে। সো এটা কেন লেস এনার্জি লাগবে? বিকজ দে আর মোর স্টেবল। তার মানে দিস ওয়ান শুড হ্যাভ মোর এনার্জি। সো আমরা যেটা করছি এখানে, উই নো দ্যাট 1 mole of Z releases that much energy. 1 mole মানে কি? 6.023 into 10 to the power 23 of these particles release that much energy. So how much would one single atom nucleus of Z release? ওটা ফার্স্টে বের করছি। কেমনে বের করছি? I took the total energy that Z releases per mole. I divided it by what? Number of particles in a mole. And I found that each nucleus of Z releases that much energy. Are you with me so far? Okay. But এই যে এনার্জিটা রিলিজ করা হচ্ছে, কার কাছে যাচ্ছে? স্ট্রনশিয়ামকে বিল্ড করার জন্য যাচ্ছে, xenonকে বিল্ড করার জন্য যাচ্ছে। But you'll find that strontium and xenon don't need all that energy. কেন? They're more stable. আচ্ছা, তার জন্য there's some extra left behind. ওই এক্সট্রাটা কোথায়? ওই এক্সট্রাটা আসছে from the binding energy that was there to hold Z together, the extra energy, right? So এটা আমরা কেমনে বের করছি? This is the energy that's released, this is the energy that was out there. দুইটা অ্যাড করে সাবট্রাক্ট করে কত আসছে? This is the energy that was released from Z. Now এনার্জিটা কোথা থেকে আসছে Z এর? Z to a particle, right? If Z is just a random particle out there, where did the energy come out from? From like interaction of electrons or the breaking of the nucleus? The breaking of the nucleus, because Z to হচ্ছে কোনো chemical reaction undergo করে নাই. And when Z broke down into a nucleus, the energy came from the nucleons inside. This is the energy that was released, right? এটা per nucleon কতটুকু রিলিজ করা হচ্ছে কেমনে বের করতে পারবো? The total energy that was released from one Z nucleus divided by what? The total number of nucleons in it, right? And that's the value that we get. This is the binding energy per nucleon in MeV of Z. Achha, and it's an average value, obviously, because different nucleons have different numbers. So আমরা যেটা করছি, so what is this number? Yeah, binding energy of Z. Okay, this one. Yeah, so the in 9.1, yeah, this is the energy released from one Z. Now Z যে energy release করতেছে, এটা কোথা থেকে আসতেছে? From the binding energy, or binding energy plus its mass? Plus its mass, right? So the total, so think of Z as like a provider of energy out there. Z কোথা থেকে energy দিতে পারবে? There are two ways Z can give energy. It can break down its watt to give you energy. particles. It can also give the energy that's stored within the what of Z, the bonds, right? So this is the total amount of energy that's released. But a total amount of energy যেটা release করা হচ্ছে, is it all becoming mass or there's a change out there? So এই যে দেখো, the total energy release কত আসছে 2.94 into 10 to the power minus 11, right? এই এনার্জিতে কি প্রডিউস করা হচ্ছে ইকুয়েশনের মধ্যে? এটাতে স্ট্রনশিয়াম প্রডিউস করা হচ্ছে, xenon প্রডিউস করা হচ্ছে, right? So what we did here was we found the amount of energy within strontium and xenon. Is you have to bind them together, right? So if you take the total energy and how much energy was released, data missing, what should that be? That was the energy that was used to what like Z together, bind Z together. So you get the binding energy here. Okay. And then ওরা চাচ্ছে binding energy per nucleon, so we divide that by 233. minus 1. Oh, এটা হচ্ছে I wanted to find Z এর হচ্ছে nucleon number. So nucleon number কেমনে বের করব? On the right hand side I had 93, 139 and 2. But আবার এদিকে 1. So wouldn't it be like 1 plus Z should be equal to 93 plus 139 plus 2. So Z should be what? 93 plus 139 plus 2 minus 1. These energies. Right. So let's first try to figure out what's 2.94. It says here it is the amount of what released, energy released in the fission, right? It's a surplus. Because what's actually happening is that you have the Z nucleus, it breaks down and it then reforms what in the process? Strontium and xenon, right? So the amount of energy that Z releases is that much, right? Out of that, energy is then gone where? In strontium and in xenon. We want to find out the energy that was given from the bonds inside it. So think of like masses taken out and masses formed. The gap in those two would be the energy that was used to bind them together, because that's not mass. Do you understand? If I take the mass equivalent of Z and produce strontium and xenon, right? That's mass becoming mass. Ideally, what should they both be? Equal, but they're not equal. So there's a gap there, and the gap is this amount there. What is that gap for? It was to bind the Z particles together. That's the energy we found here. That's the one that's released here. Okay? Because if you find the total energy released by Z, what are you getting? Let's say you find the total energy released by Z, which is this one, right? Where did this energy come from? Mass and bonds, right? But the mass doesn't stay like, as energy. It becomes what again? Mass. So we revert that and then we find what's the extra there. The extra must have been the binding energy, and that's 2.77. Okay. All right, right. Yes. So, yeah. Right. So it says a heavy aluminum disc has a radius of 0.36 meters. The disc rotates with the wheels of a vehicle and forms of an electromagnetic braking system in the vehicle. There's a name for this braking system. It's called the regenerative braking. It's like যখন গাড়ি brake করে তখন হচ্ছে it uses electromagnetism to use the energy of the car to produce electricity. So typically when a car brakes, right, what's the energy conversion? From what to what? Kinetic energy to heat, like internal energy. Brake pads below, they go to like 400, 500 degrees Celsius. Is that heat generated useful or completely wasted? Absolutely wasted. Nothing is retained from it, right? But then people started wondering, is there some way we can gain back some of it, right? So they started placing what in the wheels? Instead of physical mechanical brakes, they're placing what? They're magnets. Now they found that if you bring the magnets close, like magnets tire what's this phenomena? Why would the tire stop spinning if you just bring magnets close to a spinning wheel? Lenz's law, right? But can you break down the process for me? Yeah, so what happens is as the magnets are brought in, the disc cuts the magnetic field lines, and what's inducing the disc? EMF. And because EMF is induced, what will start to flow in the metal disc? Current. The current then will produce its own water around the disc, magnetic field, and that magnetic field will be such that it tries to what the magnetic field of the magnet. Oppose, it slows down. But to our benefit, what was actually generated in the disc? Current, right? আমরা যেটা করি ওই কারেন্টটা তো ডিস্কের মধ্যে ইভেন্চুয়ালি থেকে কিসে কনভার্ট হয়ে যাওয়ার কথা if you don't use it. Heat, গরম হয়ে যাবে. I think last class we যে coil questionটা ছিল, it all heats up, right? But আমরা যেটা করি, we take all that current and then pass it on to a what? A battery. And the battery, what it does? Recharges itself. So every time you break your car, of all the energy that you had, a percentage of it comes back again. That's why it's called regenerative braking. This is that. হ্যাঁ, এটা হাইব্রিডে ইউজ করে। হাইব্রিডে যখন ব্রেক করা দেখবো যে if you some cars ড্যাশবোর্ডে চারটা চাকার পাশে হচ্ছে ব্যাটারির মতন দেখায়, ওগুলা রিপাওয়ার হয়ে যায়। So that's basically showing how much energy is coming back. Okay, so what's the advantage of this? You can go longer. তোমার energy is not completely wasted. Some of them come back, right? আচ্ছা, এখন এখানে কি বলছি, in order to activate a braking system, এটা switch on করা হয় and it's perpendicular to this. The question was, is the question the direction of the current? আচ্ছা, okay. So question যেটা ছিল, এই কোয়েশ্চেনটা যেটা I think 2024 এ পেপার হতে পারে, I'm not really sure. ওইখানে কোয়েশ্চেনটা ছিল যে এখানে যখন যে কারেন্টটা ফর্ম হচ্ছে হুইলের মধ্যে, এই কারেন্টটা কি রিম থেকে অ্যাক্সেলে যাচ্ছে না অ্যাক্সেল থেকে রিমে যাচ্ছে, কোন দিকে কারেন্টটা যাচ্ছে বের করতে বলছে। সো এটা কেমনে করবো আমরা? সো এই টাইপের কোয়েশ্চেন আরো আছে, I've seen them many times before. Okay, it's not the first time. So there's actually a way we can solve this issue. আমি বলি কি করতে হবে। So first of all, think of this disকের উপরের পার্টটা, right? Just that part. Can you tell me which way is the upper part of the tire moving? Is it moving into the page or out of the page? Into the page, right? So আমি যদি উপরের পার্টটাকে ফোকাস করি, উপরের পার্টটার মধ্যে the movement, the force is that way, and right side কি অ্যাক্ট করতেছে? Magnetic flux, right? Or magnetic field, এটা. And what's the angle between them? 90 degree. কেন 90 degree? Because think of the circle. A circle যদি আমি হচ্ছে edge হচ্ছে, I'm talking about the instantaneous velocity. Instantaneous velocity যদি আমি ফোকাস করি, তাহলে wouldn't it be that line at the top? এই উপর দিকে একটা লাইন থাকবে ধরো, that way. মানে হুইলটা যদি রোটেট করতেছে না এভাবে, তাহলে এটা এদিকে থাকবে না, রাইট? আমরা দেখতেছি ফ্রম দ্য সাইড ভিউ, সো আমার ফোর্সটা হচ্ছে ওইদিকে যাচ্ছে, আর আমার ম্যাগনেটিক ফিল্ডটা হচ্ছে এদিকে যাচ্ছে, and they have a what angle between them at the top? 90 degree. Which way would current flow because of this? এটা বের করার জন্য we have to use the Fleming's right hand rule. কেন? Yes, it's EMF induced. EMF induced produces an induced current. To find induced current, you have to use the Fleming's right hand rule. So if you use the right hand rule here, আমি left hand use করবো and I'll reverse it. তুমি right hand directly use করতে পারো, but I found the students যেটা বেশি use করে না right handটা, use করতে একটু প্রবলেম হয়। So left hand বেশি use করে, you know better, right? FBI কারেন্টে যাই না, ম্যাগনেটিক ফ্লাক্স ওইদিকে, ফোর্সটা কোন দিকে হবে? Inwards. So if I do this, which way is the current flow? Upwards, right? In my left hand. তার মানে which way should current actually flow? Downwards. That means there's actually a current going this way. And the current then flows from the rim to the axle. And then সব জায়গা থেকে যেটা হচ্ছে, current will flow from where? The rim to the axle. As a consequence, all the currents acceleration কি করে? Accumulate করে, and then we take them all together কোথায়? To the battery. Okay. There are other ways of describing this. আমি just heads up দিয়ে রাখি, এখানে এভাবে বলছে। edXL same question does, because hybrid systems, car braking systems is like very popular right now. সব পেপারে আসে। ওদেরটা ছিল যে টায়ার যখন স্পিন করে, which part of the tire spins the fastest? Which part of a tire spins the fastest? Is rate na velocity. Rate to tire সব জায়গায় same, because omega for a tire is constant, but which part of the tire? The edge. V equals to omega r. So the outermost edge of the tire is the fastest, so it produces the what EMF? The greatest EMF. The center of the axle, right, is not spinning actually. I mean, it's just there because center to velocity is 0. So what's the EMF at the center? 0. EMF যদি হচ্ছে সবচেয়ে বাইরে বেশি হয় আর মাঝখানে 0 হয়, doesn't that create a potential difference? Where would the current flow from? higher to lower, right? So তখন হচ্ছে কারেন্ট নিচের দিকে ফ্লো করে। So ওইটাও another way of looking into this. আমরা লেফট হ্যান্ড ইউজ করতে পারি, রাইট হ্যান্ড ইউজ করতে পারি, বাট ওদের জিজ্ঞেস করে যে explain using potential difference why this happens. Okay. আচ্ছা, so তোমাদের মক কিন্তু কালকের থেকে দিতে পারবা। Your paper will be available. Also, তোমাদের previous mock papers গুলো কি কালেক্ট করছো? I have uploaded the mark schemes. তোমরা একটু মিস্টেকস গুলো চেক করে নাও। I'll discuss them in class, but আগে তোমরা একটু চেক করে দেখো what your issues are. Okay. Oh no, ওইটা হচ্ছে misplaced. I found them. I'll give them back this week. Normal class.